can, yeah, we can, but it's,
Oh,
it's on, but it should be, if you could like bring it down.
like this?
Yeah, that's already, that's good if you can keep it like
Okay,
that.
all right.
And,
Let me try.
oh, sorry. Okay, there's a pointer. Do you want to check?
This is, okay, and then this is the light. Okay, perfect.
So, right, so for the second talk, we welcome Shai, who will equally talk about Virasoro-Shapiro amplitudes.
Well, thanks for the invitation. This is my first time at one of these big integrability meetings, so it's exciting to meet this new community for me. This talk will be based on a few recent papers with my postdoc, Daliang Zhang, who will be becoming a faculty in Beijing in a few months, as well as Tobias Hansen. And of course, this whole program was started by Fernando, Tobias, and Joao a few years ago, as Maria already mentioned. Okay, so let's begin by discussing Virasoro-Shapiro amplitude. So in flat space, Virasoro-Shapiro amplitude is the most basic quantity in string theory. You know, in some sense, it's the defining quantity of string theory. And so as Maria mentioned, it's given by the simple ratio of gamma functions, where S, T, and U are Mandelstam variables in 10 dimensions. So this amplitude describes scattering of closed strings at tree level, which means the leading order in string coupling, but dimensional integral, and this is because you can actually compute this integral using the string theory worldsheet, which is why this is one of like the founding quantities in string theory. So what are some basic properties of this Virasoro-Shapiro amplitude? So first of all, it has poles in S, T, and U that correspond to the massless graviton multiplet, as well as a tower of massive string modes. Another basic property, which we're going to discuss, is the high energy limit, where S and T are both big with fixed ratio, in which case it exponentiates. This is in contrast to amplitudes in field theory, where they would also go to 0, but they would go to 0 polynomially. It's only in string theory that they go exponentially. That's one of the key differences. Another property is that in the low energy expansion, when S and T are small, it takes the following form, where the leading term would just be a field theory amplitude for graviton scattering. But then you have these infinite corrections, because you have a string, which basically correspond to these massive modes. And as Maria discussed, these are all proportional to single-valued zeta functions. These correspond to higher derivative corrections. So this would be the r to the 4 correction, the d to the 4 to the 4 correction, et cetera. Okay, so we're going to be discussing string theory in AdS. And the obvious motivation, as everyone knows, is that that is the only non-perturbative definition of string theory that we have so far. So the classic examples of AdS CFT are type 2b string theory at AdS5 crosses 5, which is dual to n equals 4 super Young Mills. You have 2a string theory at AdS4 cross CP3, which is dual to this 3d ABGM theory. And finally, 2b string theory at AdS3 crosses 3 cross M4, which is dual to some D1, D5 CFT, although we know very little about that CFT. So it's kind of the most mysterious example. So in this duality, closed string scattering in the bulk is dual to correlators of some operator in the CFT, which is oftentimes the stress tensor multiplet. For instance, tree-level scattering in string theory would be the same as the leading order 1/n term of the CFT correlator, which is what integrability people usually care about, because they care about the planar limit. So even though we have this duality, which in principle tells us how to compute AdS scattering, in practice we don't know how to do it, because AdS backgrounds involve Ramon-Ramon flux. And we don't know how to do worldsheet string theory in the presence of Ramon-Ramon flux. Hopefully in the future, maybe we'll figure out how to do that using the pure spinor formalism or string field theory. But at present, we don't really know how to do it. On the CFT side, it's also hard, because these CFTs are always strongly coupled with large n. So it seems like we don't know how to do it on either side. Nonetheless, this talk is going to be about how we've made progress using AdS CFT. So in this talk, we're going to bootstrap AdS Virasoro-Shapiro amplitude and expansion around flat space for each of these classic AdS CFT pairs that we discussed in the previous slide. And it all comes from two assumptions, this program. The first assumption is that the amplitude expanded in AdS around flat space is given by this flat space limit formula, which is basically a Borel transform of the CFT correlator. So this is an assumption, because in the strict flat space limit you can prove this, but once you apply this formula beyond the flat is given by a worldsheet integral of certain single-valued multi-poly logarithms. Maria reviewed the detailed form of these guys. And basically, by combining these two functions, it uniquely fixes the answer for the first AdS correction. So this program was first done for AdS5 by Fernando, Tobias, and Joao. And then in these recent papers with my co-authors, we generalized it to AdS4 as well as AdS3. And so it's kind of, it was kind of miraculous that it worked in AdS5, and you might have thought maybe there's some weird coincidence. The fact that it works in every possible background means clearly there's something going on. Indeed. Well, in that case, I'm not sure if you have a CFT with enough supersymmetry such that you could do this program. But in principle, I mean, this is related to Arkadi's question before, which is that the assumption of writing things as a single-value multi-poly algorithm, it might work in any background. It's just we only have enough control to check that so far in these very symmetric backgrounds. But indeed, it'd be good to maybe try for weirder backgrounds. Anyways, so the way this connects to integrability, which is what this conference is about, is that from this AdS expansion, you can extract CFT data of single trace operators at large lambda, such as the Konishi operator. And this you can directly compare to integrability. And so that's going to be one of the themes of this talk. OK, so first let's discuss what these holographic correlators look like on the CFT side. So these are CFT operators dual to graviton modes in AdS. And we're giving a very general discussion, which will work in any dimension, to show how kind of it's the same idea. So the idea is that you expand a correlator of these operators in superconformal blocks, which is fixed by superconformal symmetry. And so the 4-point function will always be written as the sum over these superblocks, one for each multiplet, plus some protected terms. I'm separating this into two terms because the protected terms are multiplets where the scaling dimension is fixed. And these are not going to be relevant for the expansion we consider, because the expansion we consider is going to be for very high scaling dimensions. And then the terms here, these are going to be the multiplets where the scaling dimension is not fixed. These are called long multiplets. So usually they're not protected by supersymmetry, and their scaling dimension can take any value. And so for specific theories, these superblocks are linear combinations of regular blocks, which corresponds to the fact that a supermultiplet is just a combination of regular conformal multiplets. And you could fix this purely kinematically. It's been done in many different examples in many different dimensions. And so remember, these are the ones we're going to care about because we care about large scaling dimension for this expansion around flat space. So the next, OK, so that was purely non-perturbative. Now we take the large n limit. And when you take the large n limit, it's convenient to express your CFT correlator in Mellin space. So Mellin space is basically a Fourier transform which respects conformal symmetry. And so you have two variables in position space, u and v. So that means you're going to be now relating it to two variables in this Mellin space, which are s and t. And so as in any Fourier transform, you're going to have these powers of u, like the one variable to the power of the other variable, for each of the two variables. These precise factors are basically what makes the Mellin space correlator convenient. But I mean, mathematically, you could have put different factors. And then you have this gamma functions that you insert into the definition. And the motivation of doing this is that in Mellin space, with these precise factors, poles in ST and U correspond to the scaling dimensions of exchanged operators in a large n expansion. So if you write down Witten diagrams, the scaling dimensions correspond to these poles. And so at tree level, we know from large n that the only exchange diagrams we should have are single trace and double trace. And so a convenient way of just taking care of all the double trace poles is putting in these gamma factors. Because then the resulting Mellin amplitude only has poles for single trace operators, which makes it much simpler. So this is just a convenient choice. OK, so first we do this exact transformation, which again is non-perturbative. Now we expand in n, and we're going to define this m of s and t as the planar limit of this CFT correlator, which is what integrability people care about. So this Mellin amplitude in the planar limit includes two kinds of terms. The first term we call supergravity is going to be meromorphic in S and T. So it has poles in S and T, which correspond to the exchange of operators in the supergravity multiplet. So this is all the single trace exchanges. All these other terms, these are polynomials in S and T. So these are not exchange diagrams. Instead, these are contact diagrams. And you have infinitely many of them. And these correspond to higher derivative corrections to supergravity. And so the coefficients of these contact terms depend on lambda, the Tuft coupling, which you could just think of as basically the AdS radius divided by the string length in some abstract sense. And basically the goal is to compute all these b's, because this is where all the dynamical information is in these b's. So this one is totally fixed, and you're trying to compute these b's for these various contact terms. If you can compute all the b's, then you totally understand this planar AdS amplitude. OK, so now, so far we've done the correlator in Mellin space and the large n expansion. Now we're going to talk about how to expand this planar correlator in flat space into AdS. And so for this, we use this formula introduced by Penedonis 15 years ago, this flat space limit formula. And so what this formula is doing is you're taking your Mellin amplitude, you're rescaling the Mellin variables by lambda, and then you're making lambda very big, where lambda, remember, is the tuft coupling, which is related to the AdS radius. So that's the sense in which you're making the AdS radius big. And then, as Penedonis showed in his paper, the way to properly take a flat space limit is you do a Borel transform. In some sense, there had to be some kind of Borel transform because, like, this is an asymptotic expansion, and so to get something finite, you had to do some kind of transformation. Borel transform is usually the thing that makes it finite. And so this formula again works in general dimensions. So this D is for general C of T dimension D. This delta O is for any scaling dimension of the external operator. A very general formula. So this formula was derived rigorously in the strict flat space limit. So the first assumption, which we emphasized before, is that this exact same formula should also apply to AdS corrections to flat space, which is a wild assumption, but as you will see, it gives the right answer. Yes? Sorry, what is delta O? This is the scaling dimension of the external operator. So you have a 4-point function of O. Yeah. Yeah, we're making them all equal, yes. So that's why it's just delta O. I mean, you could do also non-equal, but for simplicity, we're talking about equal. OK, so what does the CFD data look like when expanded around flat space? So as I mentioned, the flat space expansion you could think of physically as very high energy, and so that means you're only looking at very high dimension operators. So that means you should expand your CFD data. So this is the twist, which is scaling dimension minus spin, and this is the OP coefficient of these operators. And you expand it such that at large lambda, it's going like lambda to the quarter. So this quarter should be familiar to all these integrability experts in the audience, because that's how Konishi looks like at large lambda. The quarter basically comes from dimensional analysis, because it's basically 10 minus 2 is 8, divided by 2 is 4. And this is why these things scale like lambda to the quarter. You can work out the dimensional analysis later. And so this is the case basically in every AdS CFT example. Similarly, this OP coefficient, it's convenient to take out this factor of sine squared and 4 to the tau. The reason why you have this sine factor with all these poles is basically because you have some kind of mixing between single trace operators and very high dimension double trace operators. And so that's why you expect to have poles. But this also just falls out naturally when you apply this formula to the block expansion. So just to reemphasize, the only operators that we care about expanded around flat space are very high dimension operators. So all the protected operators, we don't care about. We just ignore them. That's why we only care about these long multiplets. So now that we have this prescription to do the AdS expansion around flat space, we can apply this to the correlator. So you have your correlator. It was written as a block expansion. So first you take the Mellin transform. Then you apply this Borel transform. And you will get the blocks expanded. And so this is what the blocks will look like when you expand them. So your block expansion, of course, you have the OP coefficient squared as usual. And then the blocks themselves, in terms of these Mandelstam variables, you expand them in 1 over lambda. And these are going to have various poles in S and T. OK, so this is the first part of the algorithm. All we've done is apply this Borel transform to our CFT correlator to expand it around flat space. OK, so the second assumption, as mentioned before, is we assume that this AdS amplitude is given by a worldsheet integral of a certain form. So in the strict flat space limit, you had this integral, but this was just 1. And so now we assume that for the AdS correction, you have the same kind of integral, two-dimensional integral, except now, instead of having 1, you're going to have an ansatz, which is the single-valued multi-polylogarithms of a certain weight multiplied by polynomials in S and T of a certain degree. So some brief motivation for why you have these weights in these degrees. So for the first AdS correction, we say you have weight 3 single-valued multi-polylogarithms. Now, why is that the case? That's basically because when you did the block expansion on the previous slide, which is purely kinematic, you get blocks which now have poles in S, T, and U. And you can just check that in the first AdS correction, you have poles up to degree 4. And so that means whatever your ansatz is here, after doing this integral, it should also only give poles up to degree 4. And it turns out that restricts the weight to be 3. Because there's some connection where it's like weight W gives poles of W plus 1. And so this is why we couldn't have single-valued multi-polylogarithms of any higher weight. In principle, you could have had lower weight, but not higher weight. If you have higher weight, you would have to go to the next AdS correction. Now, why do you have polynomials of a certain degree multiplied by these guys of a certain weight? That's because when you do the low energy expansion, you expect that the degree of these polynomials should be related to the weight of the zeta function that they multiply. So for instance, in flat space, we know that r to the 4 term is zeta of 3, and that multiplies degree 0, which is just 1. And then similarly, d to the 4 r to the 4, which is eta of 5, that multiplies s squared, degree 2. And so we assume that there's a similar correlation between the degree of the polynomial and the weight of the single-valued multi-poly logarithm once you go to AdS. So this is the motivation of this ansatz. And so now all we do is we compare this ansatz with unfixed coefficients of the polynomial to the block expansion from the previous slide, and it turns out that uniquely fixes the answer for the first AdS correction, which is kind of a miracle, because there's no reason why that had to work. I mean, first of all, the ansatz could have been totally wrong, and even if it was right, it could have been that it only fixed some of the coefficients. And so it turns out we're very lucky that it just fixes everything, and that this works in every single dimension. So now we're going to go into the specific examples for each theory. So let's start with n equals 4 super Yang-Mills. So in this case, we're going to consider the correlator of the stress tensor multiplet. So the first ingredient is just the superblock expansion. That was worked out for us by Dolan and Osborne, blessed memory, from 25 years ago. And remember, we only care about these unprotected multiplets, and in this specific correlator, they come in basically one family. So you have long multiplets of even spin, which are all in the singlet of the R symmetry. So for instance, for spin 0, this is a single trace multiplet called the Konishi, which is very popular in this community. So the scaling dimensions of these spin L single trace operators, in fact, have been computed from integrability in a series of very impressive papers by Nikolai and various other people. And so far, using integrability methods, they have the first 3 AdS corrections to the CFD data. So in particular, they have this large lambda expansion up to 1 over lambda to the 5/4, which from my understanding basically comes from taking this quantum spectral curve, numerically evaluated from any different values of lambda, and reading off a fit, and guessing reasonable numbers that should appear in that fit. So other information which is known about this correlator is you can also compute it at large n and lambda using conformal bootstrap plus localization, which is totally analytic. This is the analytic bootstrap. And this has been done to the first 3 orders, and that allowed you to compute the full correlator up to the d to the 6 r to the 4 term, which basically means 1 over lambda cubed. So this is the information we have so far. So we have precise data about the single trace scaling dimensions, and we have also precise data of the full correlator up to a certain order in 1 over lambda. Although, of course, in this limit, you only really have access to the double trace operators. This limit doesn't tell you anything about single trace. OK. So now the new results that you get, and everything here was done in the papers by Fernando, João, and Tobias. So once you fix the first AdS correction, A1, you can now extract the first 1 over lambda correction to this lowest Regge trajectory. So when spin is 0, this is Konishi. So you get the expected flat space answer. You get this kind of shift. And then you get this non-trivial 1 over lambda correction. And this precisely matches integrability. So this was one of the first non-trivial checks that this program actually makes sense, which is that you get a precise prediction, which exactly matches what Nikolai and other people did many years back. So the nice thing about this Virasoro-Shapiro program, though, is that you get not only the scaling dimension, but also the OP coefficient. And so when the OP coefficient was first computed, there was no prediction. So it was a totally new result. Since Fernando's paper came out, though, there was this beautiful work by Simon Caron-Haro, Frank, and Zara, which Frank spoke about yesterday, where they basically did numerical bootstrap plus localization plus integrability in the Plater limit, and they were able to numerically compute OP coefficients, and lo and behold, it exactly matches the prediction from this AdS Virasoro-Shapiro. So I would say there's overwhelming evidence that the assumptions used to get this answer are correct. Even more evidence comes from doing the low energy expansion of the AdS correlator up to d to the 4 to the 4 order, in which case you can precisely match it to the predictions that Silvio and I made using bootstrap and localization. And in fact, if you combine all these things together, you can actually go to d to the 8 r to the 4 order, which is the first unprotected order, which itself is very conceptually interesting. Because you would have thought analytically that maybe you could only compute protected terms, which would be d to the 6 r to the 4 and smaller. But it turns out that with Fernando's assumptions, you can go beyond protected terms and get d to the 8 r to the 4, which shows that you're really putting in something conceptually new. OK, so these are all the results for AdS 5 x 5 I'm going to talk about. So now moving on to ABGM in 3D. So now we're considering the correlator of a stress tensor multiplet with n equals 6 supersymmetry. So the superblock expansion in this case is much more complicated. It was worked out by me and Silvio and collaborators 4 years ago. So now you have several different kinds of long multiplets. So the long multiplets, they're all R-symmetry singlets, but they differ because you have 2 discrete symmetries that are relevant to this correlator. So one of the discrete symmetries is parity, and the second discrete symmetry is something we call Z, where this Z basically, it's like replaces SO6 by O6. So it's kind of an enhancement of the R symmetry, and it turns out that ABGM has this discrete symmetry, which is actually something that people weren't aware of until our paper. Okay, so we can organize the long multiplets. So when spin is 0, you have two long multiplets. They're both z even, but one can be parity even, one can be parity odd. When the spin is odd, you only have one long multiplet, which is z even and parity even. And then when the spin is even and bigger than 0, then you have three long multiplets, which can be parity and z even, parity and z odd, or parity odd but z even. So it's because of these discrete symmetries that you have different long multiplets. So this is more complicated than 4D, where you just basically had one family of long multiplets. So people have also computed the quantum spectral curve for ABGM, and so they also had some predictions at large lambda for scaling dimensions of single trace operators. So their predictions in their paper were for the odd spin guys, so this guy, and also for spin 0, z even. But they did not have predictions for z odd or these other examples, which I suspect is probably because they didn't know of the existence of the z symmetry. So hopefully now in the future, there can be predictions. I think it should probably be possible for quantum spectral curve. So also using bootstrap and localization analytically, we also have the large N and large lambda expansion, which for this correlator we have up to r to the 4 term, which means the 1 over lambda to the 3 halves prediction. So this is the data which existed prior to this work. Okay, so we do the same algorithm as before, which is that we compare the block expansion to this ansatz. It fixes the first AdS correction, and we can read off CFD data. So we can read off the twists of these lowest Regge trajectories, but we have different lowest Regge trajectories now. So we have one for odd spin, we have one, and then for even spin, we can be either z even or z odd. Now, I should note that in this planar limit, you're actually not sensitive to parity, which is why I'm not talking about parity here, but you are sensitive to the z symmetry. So this is why we get different answers for all three. So as you see, you get different numbers here, 21, 9, everything else looks kind of similar, and then this one is totally different. So for the ones for which integrability had computed the answer, we match integrability, which is very non-trivial, but we also have new predictions, which is the odd guys as well as, the even guys for z odd, as well as the z even for spin bigger than 0. So these are all new predictions. We also have new predictions for OP coefficients, which maybe could be studied using some analog of Frank's work, but now in 3D. Okay, so that's all I'm going to say about ABGM. So now we can move on to AdS3. So in this case, we consider the correlator of the unique half BPS multiplet with small n equals 4 supersymmetry that's dual to the dilaton. So here we're not talking about graviton scattering, because there's actually a simple closed string scattering, which is dilaton scattering. But it's the same idea for the most part. And so just to emphasize, there's many half BPS multiplets in this D1, D5 CFT, but there's only one of them which is dual to the dilaton. That's the one we look at. Why do we look at this specific one? Because then our results are not sensitive to this compact spacetime M4, which means that it applies to any theory with small n equals 4 supersymmetry. So in particular, it applies to either the K3 theory or the T4 theory. It's the same answer in both cases. So the first part of our algorithm, as usual, is you need to know the superblock expansion. Now, I should emphasize we're not doing like Virasoro symmetry here. We're just going to do global symmetry. We don't need Virasoro symmetry. Thankfully, the block expansion was worked out a few years ago by these authors in 2021. Similar to 4D, the long multiplets in this correlator, they all have even spin, and they're all in the singlet of the R symmetry, and then the protected multiplets we don't care about as usual. So the block expansion is very similar to 4D. One novelty of AdS3 is that the AdS CFT dictionary is a bit more complicated, in that in this duality, you have both D1s as well as F1s. Similarly, you have NS5 as well as D5. So you could turn on the flux for either the fundamental strings or its NS or its S dual. And so that means you have two kinds of fluxes in your AdS CFT dictionary. So this is the NS flux, which is k squared, where k should be an integer. And then this is the usual Ramon flux, similar to what you would have in higher dimensions. So that means a priori, our algorithm could be applying to the mixed flux case. We haven't yet specified if we're doing Ramon or NS or some kind of combination. Okay. So now, so the first part of the algorithm is the block expansion. The second part of the algorithm is we assume a worldsheet ansatz. And from that, we can read off the first AdS correction and then read off CFD data. So for the lowest Regge trajectory, this is the answer we get. This matches flat space. This is the first 1 over lambda correction. So integrability has not yet been performed for this theory. I mean, there's some partial results, but there's no quantum spectral curve, which allows you to read off 1 over lambda corrections. And so instead, we had to use a somewhat earlier approach, which is a semi-classical expansion, which was first pioneered by Arkady and then many follow-up papers, where basically you compute some classical string solution at large quantum number and then boldly extrapolate to finite quantum number. In AdS5 crosses 5, that actually matched the results from integrability, similar in ABGM, so we kind of trust this method. And so applying the semi-classical method to AdS3 crosses 3, you get a prediction for what this answer should be. And so as you see, this prediction matches our answer if we set this quantum number j, which is related to the R symmetry, to 1, and if we also assume that the one-loop correction is -1/4. And so this is like a partial check of our results, because it doesn't check it completely, but it checks some of the terms. The fact that j equals 1, this is kind of consistent with the supermultiplet you have, so that kind of makes sense. And then the fact that the one-loop correction is -1/4, that's very interesting, because it's actually the exact same one-loop correction that you get in both ABJM and AdS5 crosses 5. So I don't know if there's a reason why that's the case, but that's something we observe. And then we can also read off OP coefficients the same order. One last thing I will say is that when you do the semi-classical expansion, you can now input into that expansion whether it's Ramon-Ramon, an SNS, or some combination. And so this is why we know that our answer must correspond to the pure Ramon-Ramon case, because we are matching this answer for pure Ramon-Ramon. It would have given a different answer if it was mixed or an SNS. But that's the only way we know, because from the perspective of our algorithm, like, we never really put in the fact that it was pure Ramon-Ramon. Okay. So in conclusion, we have fixed the first AdS correction to flat space for all the classic examples of AdS-CFT, which is AdS3, AdS4, and AdS5. In all these cases, we have predictions for scaling dimensions and OP coefficients of the lowest Regge trajectory. For AdS5, this matches previous results from integrability as well as bootstrap. For AdS4, you can compare some of the predictions to integrability, and it matches, but some of them are new. And of course, the OP coefficients are all new. And then finally, AdS3 is in some sense the most interesting, because the least is known about AdS3 from integrability. So basically, everything we have is a new prediction, both scaling dimensions and OP coefficients. I didn't really talk about this so much, but you could also take the low energy expansion of this AdS correction, and you could compare this to localization. For AdS4 and AdS5, this matches the expectation. For AdS3, there's no localization, so it's just, again, an entirely new prediction. And furthermore, we get new predictions from unprotected terms for AdS4 and AdS5. So in the remaining minutes, because I started a bit late, I can talk about future directions. So first of all, it'd be nice to get higher AdS corrections. So this was already accomplished for the second AdS correction for AdS4 and AdS5. So in my paper with Daliang and Tobias, and this one with the previous paper by Fernando and Tobias, to get the next AdS correction, it's not just automatically fixed. You have to put in extra data. So you have to put in some known results from integrability and localization. That's why it's harder to do for AdS3, because we don't have any known results. So of course, it would be nice to compare more things to integrability. So for instance, the Z-odd guys for AdS4, which I think some people are working on. For AdS3, it'd be nice to get the answer for mixed Ramon-Ramon and NS flux. So actually, as of 2 weeks ago, I think we actually solved this, although we're still checking some things. And so basically, the idea is that you have to generalize your worldsheet ansatz. So because previously we were using the same worldsheet ansatz that we had used in AdS4 and AdS5, and it turns out that, like, as Lawrence had suggested to me several months ago, you break worldsheet parity once you have mixed flux, and so you want to generalize your ansatz to include parity-breaking terms. We did that, and indeed it seems to give the right answer, although we're still checking some things. Now, the reason why we think the AdS3 case is so interesting is that if you look at the pure NS example, which is just setting, it still applies to the flat space limit. In this case, in principle, the RNS formalism works. So you should be able to compute this correlator in pure NS. It hasn't been done yet, but in principle, you should be able to do it. And then, in principle, that should then give us a very powerful constraint on our ansatz, much more powerful than you have in higher dimensions where you don't know anything. And so that's why we suspect that it might be possible maybe to compute all AdS corrections for mixed flux by using this as an input. So ultimately, AdS3 might be even better than higher dimensions. Another thing we'd like to do is the large n equals 4 case, which is AdS3 crosses 1. And for this, we need a new ward identity to compute the superblocks, which is something we're working on. Finally, one thing I want to emphasize to this community is that so far you guys have applied integrability to almost all the known examples of holographic duals. So you've done n equals 4, you've done ABJM, and you've done the D1, D5 system. And then you've done various deformations. But there is one other example of AdS CFT, which is completely different from the other examples. It's not just a deformation. It has a weak coupling limit in the gauge theory. It has a tough limit on the string theory side. It has a supergravity, which is completely understood. So this theory is basically ready to integrate. You know, it has all the classic properties of integrability, and I think people just aren't aware of it. So I'm trying to advertise this theory to this community. This is a certain 40 n equals 2 gauge theory, which is dual to n d3 branes and 4 d7 branes and an orientifold. So this was first proposed by Sen in the 90s. Holography was worked out, you know, a couple years later by Maldacena, Ofer, and Fayazuddin. There was some very early work with integrability on the PP wave limit by Maldacena and on like some kind of spin chain at one loop order. But I think people just forgot about this theory because there hasn't been any work on this theory in like 20 years, basically. And so if people are getting bored working on, you know, n equals 4 ABGM and D1, D5, this is a completely new theory of which basically nothing has been done. You know, so it's virgin territory. The symmetry, so it has an SO8 cross SU2 flavor symmetry as well as the R symmetry. The SO8 corresponds to the D7 branes, and the SU2 corresponds to the orientifold. And we have some partial results about this theory. So for instance, you can study open string scattering because you have these D7 branes. And so we computed the AdS Veneziano amplitude on the D7s in this paper. And so we have predictions for like the analog of the Konishi in that open string sector. So we have this 1 over lambda expansion. Currently, I'm working on the AdS Virasoro-Shapiro amplitude corresponding to closed strings with my grad student Daniela, who's here in the audience, as well as Pietro. And one very cool thing about this theory that it's much richer than the other theories you guys have studied, because you have both open strings and closed strings in the same theory. And so there's a hope that you can actually have some kind of open-closed duality, which is something we're also looking into, some kind of AdS KLT related to what Maria was talking about. Yeah, and so the question is this theory integrable? I suspect it probably is, and I would claim this is the final frontier of IGST.
Well, let's thank the speaker. Why would it be the final frontier? I mean, is it like if we do this, then there's nothing else to do?
Well, as far as I know, there is no other example of AdS CFT, which is not just a deformation of the known examples.
Right.
Yeah. So, I mean, if you could tell me another example of AdS CFT which has a weak string coupling limit, I'd be all ears. But I'm pretty sure there is none. I mean, because in 4D, you can classify all n equals 2 Lagrangians, and there just aren't any. So this is the only theory. I mean, there's like trivial variations of it where like you add an orbifold or something like that. But it's the only truly independent theory in 4D. And in 3D, you also don't have any other examples. Because like the only type 2A example you really have is ABGM, as well as kind of like trivial generalizations of it. But you know, like, but you don't have any like actually different theory in 3D, which would have a weak coupling limit. So yeah, so I think it's just this.
Okay, questions from the audience.
Thanks for a nice talk. I want to ask the function basis in AdS4 because I know in AdS5 and AdS3 the function is pure weight 3 functions. Yeah. And it's the same in AdS4.
It's the same in AdS4, yeah.
So in some sense they are maximal supersymmetry. They have maximal supersymmetry.
I don't know if that's related to maximal supersymmetry. I mean, in ABGM you don't have maximal supersymmetry. You only have n equals 6.
Okay.
And also in AdS3, you also don't have maximal. You have half maximal.
Thanks.
Further questions? I'd have one. I recall, I think, Dorigoni talking about Dorigoni, Green, and Wang for the integrated correlator story. And they have an integral kind of formula where you have some integral over some parameter t, and it takes the form of some polynomial in the numerator divided by t minus 1 to some power. So is that related to your ansatz in the Menon somehow?
Wait, sorry. So the integrated correlator story is that you can relate some quantity you know from localization to an integral of the 4-point function. And so, you know, indeed, that is used to check some of these results. Yeah, are you asking, like, do we have such a formula?
No, I was just wondering whether it comes down from your ansatz for the Menon transform, perhaps, that they had to find that somehow.
I don't think it's not related to the ansatz. I mean, like, the integrated correlator is like some exact thing. So it's a non-perturbative thing that you can relate, you know, non-perturbatively a certain integral of a 4-point function to this non-perturbative localization quantity. You can then use it in a perturbative expansion to fix things. And so indeed, we use that, you know, to fix the correlator to some order, and then we can use that to double check our results from, you know, this AdS Virasoro-Shapiro. But yeah, as far as I know, that's the only connection.
Okay. Okay, so then we thank again and proceed to coffee, I guess.